this dynamical system, which describes the evolution of the population, is stable just for a few values of the parameters. Here we have the parameter which ensure non-chaos, chaotic behavior and non-stability.
In ecology, they use dual use.
I know about logistic map. In many mathematical papers, it is called iterative maps. So this is what I wanted in, let's say, in the large to tell you about rate of convergence and stability. And I prepared one paper. I have time enough. I copied one of my papers to show you more about the rate of convergence. So keep in mind, in connections to iterative schemes in general, with fixed point iterative schemes, this concept is essential, rate of convergence. Sometimes we don't have any information of analytic, I mean a formula to say something about the rate of convergence. Most of the applications are without such rate of convergence estimates. And I told you when I discussed these applications 2 days before, I'm not happy with papers where they deal with some application, they have an iterative method. They just take one example, one starting point, x0, and they conclude, our algorithm is better than the other algorithm. This cannot be said. Just in this particular case, our method, our algorithm is better than the others one. And then we cannot say in general, this is related to rate of convergence. Stability is very sensitive property of fixed point iterative schemes. Not many papers will find about stability, just theoretical. In my book, you'll find a few facts about stability, but not all information that is now available in literatures. These two concepts are related in some sense, but they are different concepts. They go in some sense hand in hand in the study of application of applied iterative sequences. So I presented you two concepts of rate of convergence, analytical rate of convergence, and a third one combining them. Then I introduced this new concept of rate of convergence for fixed point iterative schemes. Then keep in mind that in most situations, most concrete applications, we are studying empirically the rate of convergence. We just do experiments and we draw the conclusion that our algorithm, our method converges faster or slower, and what it happened. This is typical for mathematician. We have a problem. Let's say split feasibility problem. We take an algorithm and we prove the convergence in theory, theoretically, and we submit paper to a journal. We get, after a while, the referees, the reports of the referees. And they said, okay, results seem to be correct, proofs seem to be correct, the results seem to be new, and so on. But there is a serious objection. There is no application, numerical experiment. So what to do? We do numerical experiments to answer these objections. And I know as an editor, as a reviewer, what happens. The authors are in a very serious difficulty. So they take an experiment and they take many instances, initial values, and they just select the case when their method is better. But in some other instances, the method is not better. So this is the way, but what is not, nothing is wrong with this approach. The only fact I'm not happy with this is that sometimes they conclude our algorithm is better than the others, and this is not correct. So, as I mentioned some days before, the correct sentence will be, in this situation, in this case, our algorithm behaves better than the others. And then this is correct from all point of view. And this should be the situation, how we manage such a situation. I wanted to speak about another concept of stability. I mentioned just stability, weak stability, and also almost stability, but I did not present it weak stability. I just wanted to challenge you as future work, if you find this concept interesting, this stability is really interesting. There are no, to my best knowledge, there are no any results regarding the convergence of Krasnoselsky-Mann iteration for non-expansive mappings, for quasi-non-expansive, and so on. It will be interesting to study. As I know, this cannot be done in the general case. So we need some particular cases, we need some assumptions to get such a conclusion. So this was my presentation about rate of convergence and stability. For some of you, it could be new. It could be not usual. Maybe you did not meet this rate of convergence concept. This I did not finish. So I just want to close by showing you this paper I promised about rate of convergence, which I recommend you for reading. It's useful. No, I took another paper, sorry. This is about what happened. Did you delete the files here?
No.
Where are they?
They are just it.
No, okay, I have it on my, no.
In this. All files are in this. No, I'll find. I kept in this only.
Okay, but...
and today I have sent all the files to our participants.
Maybe I was wrong. No, I was wrong. So I did not take the right file. It's about this paper. I'm sorry. I wanted to show you some details about rate of convergence in this paper. I'll just show you. I'm sorry I did not. I had the impression in the morning I put on my memory, so it's just I mentioned here somewhere, and you should write this paper. You'll find this open. Where is it? This one. So this is the paper I wanted to show you to run on it for some other aspects, but the material I included here, it's mainly taken from this paper, and I do suggest you to search for it on a notion of rapidity of convergence used in the study of fixed point iterative methods. This will be the continuation of my main part of the present talk. So, let's try to conclude, because this is my last lecture. Please allow me to conclude all things I presented to you. Fixed point theory is extremely large, extremely large. I touched just a few aspects of it, which are familiar to me. But believe me, there are many others I would like to speak on. I didn't do this because I haven't time enough to prepare them. So for me it was easier to prepare this material from what I have. So even yesterday in the evening I realized that I could speak on some other very important aspects of fixed point theory. My intention was now to summarize what I presented. What has been to present some basic facts in metrical fixed point theory, especially related to contraction, Banach contraction and the class of mappings in this class, where the method we use is Picard iteration. It is enough to have Picard iteration. I am not very happy when I see papers that deal with Krasnoselsky iteration, Mann iteration, and many others in the class of Banach contractions. It doesn't make sense. It doesn't make sense. Why? Because this is a very simple method. We can solve any fixed point problem in the class of contractive mappings, like Banach, Kanan, Chatterjee, Chirich, and so on, almost contraction. We do not need, I've seen tens of papers dealing with such kind of iterative schemes. Okay, they are nice. They show that such kind of methods converge faster than Picard. It is clear they converge faster. There are some papers in that way. Instead of Picard iteration, they use this. Of course this converges faster because it's 2 times t. So, and if you'll we'll take t3, of course it will converge faster. What happens? We have this sequence x3 k, x3k plus 1, x3k plus 2. So what will happen? When we have t2, what happened? This will be taken into consideration, this not. So our iteration will be x0, x2, x4, and so on. If it's t3, it will take x0, x4, and so on. And normally it will be faster. But this is not a real and interesting result. Yes, it's a subsequence which converges faster. This is one fact. So in my lectures, I wanted to draw your attention to classes of mappings for which Picard iteration suffices. This is the first part of my talk. Then I wanted to show that this method also works in the larger class of almost contraction that I introduced some 21 years ago, and which is a different class of mappings because these mappings are not continuous and the fixed point set is not a singleton. We have more than one fixed point. This was the first part. The second part, I wanted to show you that for some classes of mappings, this was the class of what I call non-expansive type mappings, where we have also a metrical contraction condition. This iteration does not work, and we need some other methods to approximate the fixed point. Our aim was mainly to discuss these constructive fixed point theorems when we have a method to obtain the fixed point. Once again, topological fixed point theorems are very strong because they ensure the existence of fixed point for single-valued and multi-valued mappings under weaker conditions than this one. We don't ask map to be contraction, to be non-expansive, just to be continuous, and some other assumptions depending on the context. And then that kind of theorems cannot offer a method to approximate the fixed point by their nature, by their assumptions. So I continue with that, showing how most of these results for contractive type mappings, for non-expansive type mappings, can be transposed to multi-fixed points. This was the so-called coupled fixed point, which is a concept coming from applications, from differential equations, mainly for integral equation. And I took this opportunity to speak about the limitations of our theoretical results. So we should be all the time aware that our results have just a limited area of application, and it would be very important. Okay, when we get a new result, we are very happy. Okay, this is new, but we should be aware how large is the area of applications of this result. I've shown you on the result of Bhaskar and Lakshmi-Kantan how limited is this theorem. It's very limited area of application. So they introduced this kind of theorems in order to solve differential equations, which are in general difficult. We'll not get really new results by applying such results, as we have shown that for simple elementary problems they cannot be applied. So how to get better results for differential or integral coupled systems of equation. So in the last part, just today, my intention was to draw your attention about the numerical aspects related to using iterative fixed point methods. This is not easy. We should be aware of the fact that any method could converge fast, or could converge slowly. So we should have some information on this rate of convergence. If it is possible, we should be aware of the fact that any fixed point iterative method is linear, has linear rate of convergence. So it is not fast enough. And you should remember also what I presented, that sometimes we can accelerate such kind of methods. This is a very important and nice problem, and there is a rich literature on this, very important facts. So instead of having 10,000 iteration, if we have some tens iteration, it's a significant progress. And this would be the third aspect I wanted to point out. So rate of convergence, but last but not least, this concept of stability. So it is important to understand what does it mean, stability. In that case, for iterative schemes, this means that we have this orbit, you have seen, we have this orbit, and if you modify at each step a little bit our values, it does not go far away of the solution. This is the concept of stability. So we need stability for such kind of problems. We need rate of convergence if possible. Otherwise, we'll do experiments and we just look at them. We don't know why we have this behavior or we have this behavior for such a sequence as I shown here, I go back to it. Where is it? No, it is at the end. This drawing of the... Oh, okay, here. So here will be. So we'll have this. If we don't know what it means stability, we don't understand this behavior. Here we have non-stable map. So a Picard iteration is not stable with respect to this very simple function I wrote here somewhere. Tx equal tx squared plus x minus 1. This is a very simple function which provides a dynamical system which is totally chaotic in some situations. So I'll end. Please allow me to say some things. I thank you very much for your interest. It was really a very nice week for me. I enjoyed this course, this nice course Professor Murthy organized. I appreciate your interest. I do hope you'll take some ideas and it will be useful for you what we presented, all our team. I'm sorry I could not attend the other lectures, but I attend the lecture today of Professor Murthy and Professor Veramani. I'm very relaxed now because I had the meeting yesterday at my committee for accreditation. I had to give two reports, but I impressed them. I showed them this, not this poster, the other one. I have shown them the poster and they were really impressed about my activity. I did the reports well. It was very fine. So now I could attend today the meetings. Thank you very much. I'm heartedly thanking you. Please, please do not forget to share with me your pictures, your photos we taken together, okay?
Yeah, actually in GAN group, you are also the member of the GAN group.
Yes, I am.
So you will continue until and unless we arrive at a concrete position.
Okay.
Concrete position means to publish as a edited book yesterday I said.
Yes, but I am speaking about pics only from pictures.
Okay.
I
Pictures
want
you can
pictures
post.
with ladies. Please send me. I want to make jealous my colleagues.
Okay, yeah. Anyway, you are very smart. So they will post all the photographs what they have taken, what we have taken, our camera and our cameraman who is coming at 3 o'clock. Okay, all those. Before the lunch means once I finish this, I will finish little bit because I am more talking about the concept and some open questions only. Okay, so thank you very much, Professor. Your lecture is perfect. See, actually, Sheikh Park always says this. Sheikh Park, whenever he comes to India or anywhere he meets me, so in the audience he always says that this Murthy is my Indian adopted son. This is what for the past almost 25 years he is using this statement only. His wife also. And wherever they come or they meet me, they go to their Indian hearts in Seoul, and from Seoul they bring some sort of food for me because I am a person who is highly restricted in terms of the taking food. So this is what. So he actually said one thing why I am saying all those things. So he said one thing that suppose if there is no question from the audience, so you yourself appreciate and then say that yes, since my lecture is perfect, that's why there is no question. So I think Professor Basile, Brinde, so lecture, all the lectures are perfect. So I don't think that he has left any scope from the participants to ask. Unless you read more, you don't have the questions. you want to ask, it is a different issue, but otherwise really. And what I say is those who are already in the verge of submitting the thesis or willing to now start the PhDs, so better you work on the iteration side. So this is slowly the computational aspects are more, and now these days mathematics without computational aspect, I think now future is a very difficult. That's true. Earlier days we say that algebra means algebra, geometry means geometry, topology means topology. Where the application is your problem. My problem is not to find the application. If you want, you find out. This is what our answer is. Now we cannot give such answers right now. So thank you. Any question from the audience? Oh, Rashmi is having one question.
Sir, as you have shown a diagram. So, sir, if we have a x is equals to 5, then we draw a single line. If we have a y is equals to x, then we draw two x's, x and y. When we have a x raised to 3, that means we draw x axis, y axis, z axis. 3 roots means this in terms of graphical representation, sir, as he shown in. So that, sir, if we have x raised to 5, then how many axes we have taken and how we can draw?
No, for this one we need only the, we work in plane, but we'll skip some, we'll skip,
Parameters?
I can ask, should we have time enough to, okay?
Please carry on.
So let's see what's happening with these schemes with t to the power 3. This is the question, right? What will happen on the graph?
Yes, sir.
Okay.
Yes.
Look, we have this, and let's have this graph. This will be the first bisector. This is y equal tx, and this is the fixed point. So we start from here. Let's say here is x0. So we go this will be x1.
That will be x2.
This will be x2. This will be x3, and so on. So x1, x1 here, x2 here, and it is clear that we'll take x1 and x2 if we have t square. If we can see we approach the fixed point actually. So what happened is that we skip some intermediate if it's t square. We don't need, we represent on the same graph, but we just keep x1, and if we have t square, if we have t to the power 3, then we'll skip 2. And we'll have only one x0, x3, and this is a subsequence. And this is a subsequence, of course, it will apparently converge faster because we don't take the intermediate. But the rate of convergence is the same, actually. We did not improve the, in this way, we did not improve the convergence. It's exactly the same because we can prove it's just by skipping some, we leave some terms, we don't improve. Is that your question? Okay.
Also, sir, you have drawn trajectories. So why drawn their trajectories? And what kind of that? Orthogonal trajectories or something else, sir?
You mean this this one?
Yes, sir. And there is intersection points, then we have fixed points. So why you have drawn these trajectories?
Here.
Kind of, yes, sir.
Here, as I explained, no any trajectory will intersect the other one.
Sir.
Because if it will be some intersection, then we'll get the fixed point. Look, if we have, let's say, t of xn equal t of xn plus 1, then we have exactly reached the fixed point. So no one, once